Transparent bridging. In the early days of network connectivity, LANs were very restricted in their size. The reason for that was there was a lack of networking devices that could divide a collision domain or make intelligent forwarding decisions. Bridging addressed both of those issues. In fact, there are many forms of bridging, but transparent bridging is the one that we're going to cover today. In this nugget, we're going to start off by defining exactly what transparent bridging is. And then we'll take a detailed look at the operation of a transparent bridge. We're going to follow that up with a talk about the multicast limitations that are inherent in transparent bridging. After that, we're going to look at the frame modifications that occur whenever a packet goes over a transparent bridge. And then we're going to end up with a discussion on transparent bridging and its effect on the collision domain. Transparent bridging was first developed by DEC in the early 1980s. Now, DEC stands for the Digital Equipment Corporation. What they did after their initial development is they went to the IEEE, which is a standards organization. Let me put my other E in there. And they said, can you put this in with the 802.1 standard for bridging? And they did. So here is the standard for transparent bridging now. All right, what we're going to do in our discussion of defining transparent bridging, we're going to take it in two parts. First, we're going to discuss a bridge and what it does by definition. And then, because we know there's a couple of forms of bridging, we're going to look individually at the transparent type of bridge and why we label it transparent bridging. A bridge is first and foremost defined as a layer 2 network operating device. All right, what do I mean by the layers? If you recall in our OSI model discussion, there were 7 layers. The bottom layer was the physical layer. Layer number 2 was the data link layer. This is where our bridge is going to operate. And because of that, it is completely aware of physical addresses. We also term those physical addresses as MAC addresses. They reside here at layer 2, so that's how it makes its decisions on forwarding or filtering packets. What else does that mean? It means it doesn't have to regard or be dependent on anything in the upper layers. So the next layer we have here is the network layer, and that's where logical addressing takes place. If we're running IP, an IP address is here. If we're running IPX, an IPX address is here. It doesn't care what's up here. It's going to operate at this level only. And that is a big blessing in the way that it is able to, again, forward and filter its frames. Another advantage of a bridge operating at layer 2 is that it can support 2 networks or bridge between 2 networks that have different physical media requirements. In other words, I can have a star topology here, and in that star topology, run UTP cable into my bridge. On this other network, I may have an old 10-base-2 network that runs coaxial cable. This can be accomplished. All I need to do is have a bridge with the correct connectors. All right, the next thing I want to move into is a bridge has 3 functions. The first is a learning function, and then a forwarding and a filtering function. These functions kind of go hand in hand. This is the intelligence of the bridge, where it will use its awareness of the MAC addresses or the physical addresses to either decide to forward or filter a packet down a certain port. And the way it does that is by learning the network. We're going to cover that in more detail later in this nugget. All right, now let's move into our definition of transparent. It is as simple as saying the host or the clients, here we see N1 for representing a PC and N2, will act exactly the same whether a bridge is between them or not, and that's a transparent bridge. So let's look at how that might happen. If I have N1 that wants to send a packet over to N2, the first thing it's going to do or be commanded, let's take a protocol example. If we're going to set up a telnet session, and in that telnet session, we supply an IP address that we want to connect to from N1. It's the IP address of N2. What it's going to do is recognize that that IP address is on the same local area network. And once it does that, it's going to ask and send a broadcast out here to say, who is this IP address? And please send back a MAC address. Because if you recall from earlier nuggets, we talked that N1 and N2 are going to talk to each other based on a MAC address. The logical addressing is simply to help with routing and get us across a large network like the internet. Once 2 PCs are on the same local area network, they talk to each other via MAC address. All right, so with that example, once I know the MAC address of N2, I simply forward a packet or a frame out onto the wire. It is going to have a destination MAC address of 00065B followed by 6 2s. It's going to have a source MAC address of 00065B followed by 6 1s. Okay, now let's interject a bridge here. That is so that we can support other devices. other than just a crossover cable right here between two devices. Once we do that, that packet going from N1 to N2 does not change in the least. It still has the same destination MAC and the same source MAC. The bridge is not addressed at all. Throws it onto the wire, and now we can make intelligent decisions here on the bridge based on those MAC addresses and whether it will filter or forward. And in our next discussion, we're going to go into detail on how that decision is made. For the sake of our transparency example, I showed a bridge here that divided clients or hosts from each other, N1 from N2 and from N3. In most applications, though, a bridge is going to be used to divide two or more local area networks. So let's define what a local area network is. It's a number of PCs that are connected by one layer 1 networking device, the same layer 1 networking device. So a layer 1 networking device is either a repeater or a hub, which is simply a multi-port repeater. Repeaters normally have one input, one output, and they can connect back-to-back two PCs at layer 1. What does that mean? It means that they operate here at the physical layer. They have no awareness of MAC addresses or anything else in these layers above. Okay, so it only makes decisions based on getting a packet in and knowing that it won't forward the packet back out that same interface it came in on, but it'll send it out every other port that it has available. So simply it's going to broadcast every time it gets a frame or a packet coming into a port. All right, so a number of PCs connected by one of these two devices is called the local area network. A bridge will be used, and we'll show you in this next diagram, to connect two or more local area networks. So here we have it. You can see one of those layer 1 connectivity devices here and here. It allows N1, N2, and the bridge to be on this same shared space. And the same thing on this side, N4, N3, and the bridge to be on this same shared space. The simplicity of these layer 1 devices doesn't warrant further discussion, but you do need to be aware of their placement in our diagram as we discuss the operation of bridges. All right, let me familiarize you with what we have here. What I'm going to do is I'm going to number the frames as they're transmitted from a specific device to another. I'm going to label which device is sending, which device is intended to receive, and then the bridge's actions, and explain why the bridge is taking a particular action. Another thing that a bridge keeps is called a bridge table. Now it keeps this in a volatile section of memory. So if you reboot the memory, this information will be gone. But what it does is every time it receives a packet in a specific port, let's say in this port here, going this direction, it is going to know or mark down that that MAC address 00065B111111 existed out of that specific port. So it's going to list the MAC address here and the port number. It's going to continue to build this table because this is how it makes its decisions to forward or filter. And as you can tell, this is the learning process. So this discussion is going to take into account the three main capabilities that we listed on the last whiteboard of a bridge, and that was learning in this area, and then once we have the learning down, making this decision of forwarding or filtering frames based on the information it used here in the bridge table. So let's kickstart our network and start sending frames. The first frame we're going to send is frame number 1, and it's going to be from N1, which is this host here, with a destination of N2. Remember, in the frame, the source is going to be this MAC address, and the destination will be this MAC address. All right. Recall that this layer 1 device has a native operation, and what it does is it receives a frame on one port, and what it does is it sends that frame out every other port that it has, because it's not intelligent enough to be aware of these addresses because it's on the layer above where it operates. So the bridge will see this frame, and so will N2. N2 will have no problem with it. It's going to process it because it is destined for N2. But now we've got to talk about what is this bridge going to do. As we're talking about the bridge, it's going to be important that we label the ports. It has two ports, one here and one here. This is going to be port number 1. This side will represent port number 2. The significance is in the bridge table here. All right, so as soon as I receive the packet, I am going to forward the packet. Why does that happen? The only thing the bridge has to work off of for its intelligent forwarding or filtering is this bridge table. Right now, it is not populated at all. So its default action, if it doesn't find the destination MAC address in its bridge table, is to forward that frame on out the other interface. Kind of crazy, right? Because it's going from N1 to N2, but this bridge is going to send it out to N4 and N3. Overhead on this local area network and wasted CPU time on N4 and N3. But this is just the beginning. It's a learning device. It will learn. And what did it learn in this instance? It learns based on the source MAC address and the port. So N1, which is 00065B, followed by 6 ones, is out of port number 1. Now to keep this short, all of these MAC addresses have the same 00065B beginning. So I'm going to leave that off. So let's just say the MAC address of N1 was learned, and it is out of port number 1. Let's move on to the second frame that is going to be sent. This is going to be sent from N2 to N1. It is a response to the packet and frame we just sent here. So what's going to happen? That native operation is going to send that second frame to the bridge and to N1. N1 will process it. The bridge is going to say, let me consult my bridging table. In this instance, the source MAC address is going to be here. The destination MAC is right here. So what happens? It looks at its bridge table and says, hey, I know this MAC address, and I know it exists out of port number 1. So what do? I am going to filter. Told you it would get better. So now we don't have that wasted packet over here, where if we had a layer 1 device, combining all of these 4 network devices, they'd still have to see it. So we're already seeing some advantage of having our bridge introduced. And as we've already discussed, the benefits that we see by using a bridge is based on its ability to learn. So let's find out what we learned in this second frame. We learned that the source, which we see here, the source MAC address, exists out of port number 1, just as N1 does. So you can have multiple MAC addresses existing out of the same port when you're dealing with a bridge. So here's port number 1. Now before we move on to the next frame to send, let me take a step back. You might have noticed that I purposely am interchanging the word frame and packets to describe the unit that is being sent across this wire. Let me tell you why. In a strict definition, layer 2 units are called frames. Okay? And layer 3 units are called packets. Now, in literature, including literature on the Cisco site, you're going to see this unit that's sent over the wire referred to as a frame in some instances, and also it can be referred to as a packet. Let me let you understand why that is allowed, or the explanation for why that happens. When you have a frame here at layer 2, it doesn't have what they call a preamble and a start of frame delimiter. Those two pieces are added when you're going out on the wire, and they're added so that the two devices that are talking to each other can use the preamble time to synchronize, and the starter frame delimiter announces, hey, the frame is about to start. So once you add these two pieces to that frame, they're saying this is no longer strictly a frame, so we're going to call it a packet. Okay, so the only reason I let you know this is to avoid confusion. If you're reading other documentation in preparation for your CCNA, or even preparation for what you're doing at work, keep in mind that these two can be used interchangeably in reference to the unit that is going across this wire. All right, let's move on to the next frame, and that's frame number 3. Here we're going to have N4 as a source and N2 as a destination. So we're running from this host across our bridge to this host. What's going to happen? We can do nothing about this layer 1 device forwarding the frame that's sent out from N4 over to N3. Simply its native default environment, it's going to do it. N3 is going to have to discard that packet. It's a little bit of wasted CPU and some overhead on the network, but there's nothing we can do. The bridge will receive it, and once the bridge receives it, it's going to look at its bridge table, and it's going to say, my source MAC is here, my destination MAC is here. Do I have that in the table? I do, and it's out port 1. I received this frame in port 2, so I'm going to forward. And that forward is going to take place and go out eventually to N2. The next frame we're going to get to is frame number 4, but we can't forget what was learned in frame number 3. This MAC address for N4 is now learned to exist out of port number 2. We have 3 of our 4 hosts on this network documented in the bridge table. Let's move on to frame 4. This is going to be the response from N2 to N4. All right, so as N2 sends a packet out, it gets to the bridge, it consults its bridge table, and the destination MAC address is here. It finds it, it says it's out port 2, I received this frame on port 1, I forward. All right, frame number 5. What we're going to do here is have a frame run from N3 to N4. These reside on the same local area network. Again, the definition, the same shared level 1 networking device. So as that packet goes out of N3, the bridge is going to see it, as well as N4, who will process and be able to respond. When the bridge gets it, it consults its bridge table and it says, the destination MAC is this, I see it here, it exists out port 2. I received this on port 2, I am going to filter. So it doesn't send anything and it says, but wait, I learned something as well. The MAC address for N3 exists out of port number 2. Now we have our bridge with the knowledge of every host on these 2 local area networks. All right, and it will keep that knowledge up to the point that the bridge has lost its power because it's in volatile memory, or the timeout value associated with keeping this information. All right, so let's keep on moving forward. What's going to happen in number 6? This is where we're going to have N4 respond to N3. Same action as before. N4 sends the packet out, the bridge gets it, it looks at its bridging table, the destination MAC address is here, so I filter. And now that we have knowledge of the entire network, this gets pretty easy. So let's go for our 7th frame, and this is going to be a bit different. N1 is going to broadcast. Now the broadcast address, if you recall from our discussions on layer 2 addressing, is simply all Fs. 1, 2, 3, 4, 5, 6 sets of Fs. And what the intention of a broadcast is to get to every host on our local area network. Now with a bridge, it forwards broadcast packets. So that packet will go from N1, go to N2 because of the default operation here, get to the bridge. It consults its bridging table and it says the destination MAC address of all Fs. Do I have it listed? No, so my default action is to forward this out. This layer 1 device will forward it to both devices. So N1 effectively sent a broadcast to the other 3 members, even though the bridge defines the 2 local area networks as 2 separate networks as far as collisions are concerned. Most easily stated, a bridge does not divide a broadcast domain. So 2 LANs on each side of a bridge are still one, this whole area here, one broadcast domain. All right, let's move into multicast. So far we've talked about unicast packets, which means from one host to another, and we've talked about broadcast, which means from one host to every host on the local area network. Multicast were created and defined as a way of N1 having a group or a shared interest with, let's say, N2 and N3, but not N4. And when it sends a packet out to a multicast address, which is a special address, it's not the all Fs address for the broadcast, and it's not the specific unicast address, but a special address that they will answer to. It could send it out, and these 2 devices would know what to do with it, and N4 would simply discard it, saying, you know what, it's not associated with me. Ideally, N4 would never see that frame. In fact, it would go out from N1 over to N2 and to N3 only, not wasting the CPU time for N4 to look at the MAC address, understand that it's not its unicast address or its specific physical address, and it's not an address for a multicast group that it's a member of, and then discard it. All right, the bridge is not capable of doing that, and let me explain why. Once we have our bridge table fully populated, that is to say that it has an awareness of every host on the network and its associated MAC address and the port that it exists out of in reference to the bridge. Again, port 1 here, port 2 on this side. Once it has that whole awareness, we will send a multicast frame. Here's our first. We're going to source it from N1 here. Now, the 2 address is going to be a special multicast address, as we spoke of earlier. Let's use the example of 0100 0 Charlie, 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 Charlie. You may recall that this is the MAC address used for multicast in support of CDP, which is part of another nugget. When that is sent out, the bridge is going to receive it here on this port. this layer 1 device has already forwarded to N2. So N2's received it. When the bridge gets it, it consults its bridge table. This address will never be part of this bridge table, and let me tell you why. Remember, the process of learning is to take the source address on packets and mark that MAC address down and the port that it came in on. The multicast address is never used as a source address, so it can never be part of this bridge table with its native operation. So what it's going to do is consult the bridge table, find out that it's not existing, go with the default operation, forward it out here, hits the layer 1 device, goes to N3 and to N4. So everybody's going to see this multicast packet or frame, and so it doesn't save on the bandwidth as we had intended for multicast. So far in this nugget, we started by defining what transparent bridging is, then we took a detailed look at the operation as it divided LANs, and then we just talked about multicast limitations that are inherent with transparent bridging. Now we're going to look at frame modifications. When we talk about frame modifications, we're talking about the bridge, which I'll draw out here, being in existence between two hosts. We'll start with N1 and N2. And as that unit moves out of N1 over to the bridge, what's going to happen? This is the unit in its entirety that leaves N1. Again, if you remember, in the strict sense, a frame is defined as a layer 2 unit that has the destination MAC address, which is the physical address, the source MAC address, a length field, the data from the upper layer protocols, which can be between 46 and 1500 bytes, and then the FCS. This is a frame check sequence. Simply put, it's an algorithm that they run when you send the packet and when the destination receives the packet. Make sure that thing matches, and that way this part, this data portion, hasn't been tampered with. Now when you send it over the wire, the preamble and the start of frame delimiter are added for synchronization. Okay, so as soon as the bridge gets this, it's going to take the preamble and the starter frame delimiter and drop it right here. It's simply going to deal with this layer 2 strict frame. It's going to process that frame. If it decides to forward it out this other port, it is now going to attach a preamble and starter frame delimiter of its own and then send that new unit out to N2. The preamble and the starter frame delimiter are always the same combination of zeros and ones that are transmitted over the physical media. That's why it can be taken away and added without an understanding of what was dropped, because this never changes, so it simply adds the default here. So far, we've taken a look at the bridge and the effect it had on a broadcast domain. It had no effect on it. The broadcasts were forwarded through the bridge. Now we're going to talk about the effects on a collision domain. To start that out, though, we've got to talk about what a collision domain is, right? All right, so my illustration here on the top has 1, 2, 3, 4 hosts on a network, and there's a shared bus here. This shared bus can be in a star topology where you have a hub in the center and spokes to the 4 devices, or it can be the older style 10-base-2 network where each of these devices drop off of this network, and then you have terminators on each end so that this wire is the shared piece. In this case, the shared bus exists in the hub. Either way, though, this is what we're faced with, and the opportunity exists for N1 to send out a packet at the same time that, let's say, N2 does. If they go out at the same time, they will meet on this wire somewhere, and when they meet, this is called a collision. A process occurs then where everybody backs off, an announcement is made that there was a collision, and retransmissions are tried. All right, so that's a collision. What we use to avoid collisions is called CSMA CD. It will be covered in detail in another nugget, but for the purpose of this discussion, carrier sense multiple access collision detection. It simply means that N1 is going to wait for a carrier sense, in other words, listen on the wire, then transmit when it hears nothing. At the same time, after it transmits and during transmission, it's going to have its ear to the wire still listening for a collision. All right, so this is what happens under normal operation without a bridge. What a bridge is going to do is come in here and set in between N1 and N2 and N3 and N4. When that happens, the collision domain now exists in 2 parts. Where this was one collision domain across this entire wire, now there is 2 collision domains. Let me explain why. If N3 transmits, there is no awareness of that transmission on this wire over here, because the bridge segments that piece. When N1 transmits, again, same thing. No awareness here that N1 just transmitted. It will go across the wire, find everybody here. In this case, there's only N2 and the bridge for that packet delivery. All right? Now, if there was a possibility that these two could collide, then we could have one collision domain. But because there isn't, and we have a divider, we have two collision domains. This division of collision domains proved to be a big advantage. Remember when we had a discussion about the early days of networking, and we talked about the restrictive size of the networks. That was due to the fact that only so many hosts can exist on one collision domain. Once you bring a bridge in, you create two collision domains, you've doubled the number of hosts that you can accommodate now on a network connected together via a bridge. You connect these bridges in series, and you've added even more hosts. Of course, there are other network devices that can be added, like routers, that will expand your network even further. But bridges, for their day, were a big announcement, and the scalability of networks was improved drastically. In this nugget today, we started by looking at the definition of transparent bridging. We understand it to be a layer 2 device that is aware of MAC addresses and has three main capabilities: learning, filtering, and forwarding. The transparency part of this definition is in reference to the fact that as hosts or clients on a network sending packets to each other, it doesn't matter whether a bridge is in the loop or not, it sends it exactly the same. Then we moved into a detailed look of the operation where we saw the learning, the filtering, and the forwarding exactly as it happens in reference to a bridge table. After that, we looked at its limitation in multicast. It cannot support multicast because the multicast address will never be a source address of a packet and included in the bridge table. So the default action is to broadcast those packets out every port except the one it was received on. Next, we talked about the frame modification that takes place as a frame goes across the bridge. And we ended up with a discussion on collision domains and how bridges do divide collision domains, and because of that, scalability is enhanced in networks. I hope this was informative for you, and I'd like to thank you for viewing.